Right. So I realized, and I was very happy about this, that at least with some of the things I will be talking about, Clark is going in this direction a little bit, which is great because that means I don't have to cover that part. I want to talk about the following statement today. You might have already seen it. Peter has talked quite a bit about it as well and proven a version of this theorem here. But the following statement: taking infinity categories of exit paths, whatever that is, should induce an equivalence between a homotopy theory of topological stratified spaces, whatever that is, and the homotopy theory of certain infinity categories, so-called layered infinity categories, whatever that is. At the end of the talk, I hope at least these red parts will be clear. And what I specifically want to do is I want to do some presentation here, not in the literal sense of me standing here presenting it, but presenting it in the sense of, like presenting an infinity category. So maybe before we go into the depths of stratified things, let us just take a quick look at the classical homotopy hypothesis, which should say something like, okay, there should be an equivalence between the homotopy theory of spaces, or maybe anima if we're cool nowadays, and the homotopy theory of infinity groupoids, right? And at least nowadays, a lot of people take this to be a sort of formalization of this philosophical statement, namely the statement that the classical realization and singular simplicial set adjunction between simplicial sets and topological spaces induces a Kahn-Coulomb equivalence, or is a Kahn-Coulomb equivalence. Now, why do we call this thing, why do we call this formalization of the homotopy hypothesis? I would say it's for several reasons. First off, nowadays, which is, and maybe if we go back, homotopy hypothesis, oh, that's not working, sorry. When was this asked? Grothendieck in 75. The answer is from 67, so there's something wrong here. Right? Nowadays, we like to think of Kahn complexes as infinity groupoids. And there are reasons for this. We can go there in a second. Let me maybe use the chance to, as well as I could piece it together from pursuing stacks and the NLab and so on, tell a short historical anecdote about this. So I think Grothendieck started thinking about this in 75 when he was trying to develop higher versions of stacks. And he wasn't super familiar with homotopy theory. So he asked a student of his, or former student, Lawrence Breen, in a letter and said, well, I think there should be this type of correspondence, right? Whatever an infinity groupoid is, it should somehow be related to homotopy types. And Lawrence Breen said something like, well, I also don't know for sure, but maybe Art Quillen. He would know. And Grothendieck wrote a letter to Quillen, I think a few years later, and sadly Quillen never got back to him, which he wasn't happy about. Like you can read his Pursuing Stacks, he was not happy about not getting an answer. And then years later, there was this correspondence with the Bangor group between when Grothendieck was sort of returning to mathematics a little bit. So with Timothy Porter and Ronnie Brown. And it seems that Timothy Porter, he asked the same question to Timothy Porter, and Timothy answered, oh, but isn't that thing you're looking for just the Kahn-Quillen equivalence with Quillen's theory, like Quillen's model structure on simplicial sets and so on? And Grothendieck was very unhappy with this answer, which might have partially been because Quillen didn't answer him, I'm not so sure. But no, probably it was because he had a different idea of what an infinity groupoid should be, right? This meant something different to him. And of course, it's the problem with philosophical statements as the one before. If we want to turn them into something mathematically rigorous and prove them, we have to sort of decide what models what, right? And this statement, the homotopy hypothesis, whether it's proven or a hypothesis, depends what you put on what side, of course. And in this case, I'd say mainly due to the work of Jayal and Lurie and many other people, we now think of Kahn complexes as the infinity groupoids internal to the model for infinity categories, which is quasi-categories, right? So in this language, these are actually the infinity groupoids. So this side of the equation makes sense. And then on the other side, why do we think of this thing here, topological space and weak homotopy equivalences as homotopy theory of spaces? Maybe a very naive question, but we can ask that question, of course. And I would say this goes back quite a bit further, right? This goes back to Whitehead. Ultimately, Whitehead's theorem tells you that this theory here, we can equivalently just think of it as CW complexes up to homotopy, right? So Whitehead's theorem, or more generally the Quill model structure on topological spaces, tells you you can really also think of this as CW complexes up to homotopy equivalents. And so this is really what people classically meant by the homotopy theory of spaces, like classical algebraic topology. Right? The reason I'm telling this story is just so we can return to it a little bit later on when we're doing the stratified part. But I would argue there are a few things we should recall about this equivalence, which are quite nice. The first thing I really like about it is we have this nice presentation of it in terms of this really easily understood one categorical functor adjunction, which then induces the equivalence on infinity categories. There's no need to derive. That's, of course, because of the specifically nice model structures here, but I don't have to do any type of deriving construction to go to the infinity category level. And then on the side of topological spaces, we know how the homotopy theory of spaces interacts with geometry, right? That's partially done by the Quill model, which of course tells you that fiber bundles, something that people in the geometrical setting like, are fibrations, or that manifolds are actually cofibrant or bifibrant, this type of setting. So we have extra tools that help us relate the geometry, the topology to the homotopy theory. And the goal for today will be to establish a similarly nice situation for the stratified homotopy hypothesis, which in the way I put it on the board was first proven by Peter, and we'll return to that later on. Okay, so I'm not expecting that everybody is familiar with what stratified spaces are, or why one should do stratified homotopy theory. So let's start with something extremely simple. Here we have two singular spaces. They have singularities. There's one here, and there's one here. Not manifolds, not even homogeneous dimension over here. And these two are homotopy equivalent. I'm not sure if you've ever tried this out, but if you sort of take the pinched torus over here, which is a torus where you collapse one of the S1s to a point, and now you pull this pinching point out, you end up with an S2 with a filament attached. You move over the endpoint of one of the filaments, and you get the space over here. And now if you are trying to do any type of classification of singular spaces, maybe up to homotopy theory, then you can already see, well, even in low dimension, homotopy types can't really tell things apart. They're especially bad at recalling this type of local singularity information. Maybe from a geometrical point of view, one would want a version of homotopy theory that recalls this type of information, right? And the way people classically have dealt with such singular spaces is by using so-called stratifications. And very classically, a stratification of a space really meant you have something that's not really a manifold, but it has some singularities in there, but it's built from manifold pieces, and you decompose your space into manifold pieces. That's what historically a stratification meant. Now, in all of these types of scenarios where these stratifications arise, often the so-called frontier condition is fulfilled. And this condition just tells you that, okay, you have your decomposition here, and whenever one of the pieces intersects the closure of another, then it's already actually contained in the closure. That seems to show up in the type of stratifications that arise, for example, in algebraic geometry. And then under these conditions, the closure, this indexing set here has a natural poset structure induced by this relation. And it turns out that the map that associates to a point X, its index, is actually a continuous map with respect to the Alexandrov topology on the poset, which is the topology where the downward closed sets are closed. Okay, so closed under the relation down. And this led to the somewhat more modern definition of a poset stratified space, which is, I think, the one that's mainly in use now, where we just define a stratified space as a space X together with a continuous map into a poset with the Alexandrov topology. And then the
Can you go back to the previous picture?
Yep, I can.
Does this picture satisfy this condition?
It does, yeah, I think so.
But doesn't the yellow intersect the blue?
No, I don't see where the yellow intersects the blue.
These are open pieces.
These are all open pieces, yeah. It's disjoint. Yes, it's a disjoint, I should have said. It's a disjoint decomposition into pieces, yeah. You can see this from this definition immediately, because in this definition, the pieces, the so-called strata, are just the fibers of the map, and these are clearly disjoint, right? So here, this issue doesn't occur. Maybe if we look at these two examples, we could just stratify them over the poset with two elements here. We just send this point to red and everything else to blue. And then you can already figure out that this homotopic theoretically recalls a lot more information. For example, here we have two path components in the blue piece. Here we only have one. So you can already tell them apart. Okay. Maybe there's a caveat here. Namely, what I just described, a lot of people who are sort of on the more geometrical algebraic topological side, they would be unhappy with calling this a stratified space. It sort of depends on how old school you are. There are many other definitions of what a stratified space is, which now end up adding adjectives to this, right? I certainly won't go through this complete picture. Maybe let me just tell you, all of our algebraic varieties can be stratified nicely as so-called Whitney stratified spaces, sort of a smooth version of stratified spaces. And then all the way over here, we have these so-called conically stratified spaces and the homotopically stratified spaces, which I will get to in a second.
Sorry, where were we in that diagram?
Well, we're a poset stratified space, so we haven't added any of the adjectives at here yet.
Okay.
So we're like, we'll have to add some later on. But we're not. I mean, here you put some extra structure on, right? So like an algebraic variety isn't intrinsically stratified. You have to perform some type of procedure to stratify it, right?
All of these can be realized as this.
All of these fit into this setting, and now we get to sort of the more sensible, or more geometric definitions of what a stratified space is.
Excuse me.
Yeah.
Is the yellow portion part of the space?
The yellow, this, yes. Yes, no, this is just a pinch torus where I glued a D2 in. So I just glued a disk into the pinch torus, just so I have a more interesting poset over here. Just so to show you not all posets are linear. That was the only point I was trying to make here. Great. So one example of stratified spaces people have considered it a lot are the so-called conically stratified spaces. And what this roughly means is, well, first we define what the stratified cone is. We start with some stratified space, stratified over PL. We add a minimal element to the poset, so sort of minus infinity. And then we stratify the cone by sending the cone point to this additional minimal element. And everywhere else, we use the usual stratification. And a space which locally looks like the cone on another stratified space, cross and open, is called conically stratified. So for example, here at this point, locally, we look like the cone on this glasses type of stratified space, right? If we go over here, we look like a product of the reals or open reals, open interval with this type of 3-point space.
So L can be any?
L can be any stratified space for now. Now, if you want to go more geometric, you might require that the strata are also manifolds. And you can do some type of inductive definition, then you end up with what people call a topological pseudomanifold, for example.
Sorry. Is cone on the empty space a point, so
Yeah.
everything is conically stratified?
Every normal space is conically stratified. Every trivially stratified space is a conically stratified space with the cone on the empty set. Exactly, yes. That works. But, I mean, otherwise it depends on the stratification that it chooses, of course, right?
Because U is just a space, not a.
Yeah, just a space. Every space is a conically stratified space, I guess. Right. And for example, algebraic varieties fit into this setting. They admit nice, reasonably canonical stratifications, which you can stratify in this type of conical fashion. Maybe another example I want to look at is the stratified simplex, because that will show up quite a bit. If I have an n simplex, there's topological n simplex, I can stratify it by sending a point t0 to tn to the maximal I where ti does not vanish. So the interval I would stratify like this: 1 point in the red stratum, 1 in the blue, and the 2 simplex would look somewhat like this. And these will show up quite a bit later on. We will also have an extra definition here for flags in P. So these are, if I fix a linear sequence in P, so-called flag, then I write delta ISP for the n simplex, which is stratified by first using this stratification above and then sending the index I to PI over here. Okay, so if we want to do homotopy theory, at some point we'll have to define what a map is, and the map in this context is the obvious thing, right? These are just arrows with the targeted poset, and stratified maps will just be arrows in this arrow category. And now, if I fix the poset, I will just write strat P for the category of poset stratified spaces over some fixed poset P, where the maps here are the identity. Okay. And now, in this type of context, I have now sort of given you the object, I've given you maps. I can ask myself, what is a good homotopy theory of these type of objects? There are all sorts of reasons why I would want this. Constructible sheaves will show up maybe at some point in Clark's talk. But there are many other reasons. You could want to do isovariant homotopy theory, so a version of equivariant homotopy theory where you sort of keep track of the stabilizers. You could want to do surgery theory to classify all stratified spaces, and then you want a good notion of homotopy type. Intersection homology theories naturally live in this setting, compactifications of moduli spaces, and even like within topological data analysis, you can use these type of tools to sort of get stratified information out of point clouds. There are all sorts of reasons to look at this. So let's maybe try the most naive thing to write down what a stratified homotopy theory should be. And the naive thing, of course, would be, well, I just define what a cylinder is, and then a homotopy is whatever a homotopy is with respect to the cylinder. And what I can do is I can just take the product of a stratified space with the interval and then stratify it by projecting to x and then to px. So for example, this stratified circle here with a fake singular red point just goes to the cylinder stratified like this. I can certainly do this and then just say, okay, stratified homotopies are homotopies with respect to this cylinder. A stratified homotopy equivalence is a map which is invertible with respect to this cylinder. I can naively do this. We can look at a few examples. Well, certainly everything is stratified homotopy equivalent to its cylinder. That works. I can tell these two spaces apart. That also works. The easiest thing to look at is the number of path components of the blue piece, which should be preserved under these type of stratified homotopy equivalences. They differ. But it turns out this isn't really a good theory to work in. And we can see this already from these type of simple examples here, where I took the singular point, the red point, and I slightly thickened it. And these two are not stratified homotopy equivalent. This might be a bit surprising to you because I think intuitively often people think of stratified spaces with two strata as pairs of spaces, right? And there, these two things would be equivalent as pairs. This is not true in the stratified setting. Just try to construct a map from here to here of degree 1. You won't be able to do it in a way that preserves the coldness. And so the stratified setting is sort of a bit too rigid. And this is partially because this thing is not a conically stratified space. It's not a nice geometric example. And now, of course, we need some more refined approach, right? We have all of these great tools of homotopy theory available. How could we do something slightly smarter, like localize a smarter class or restrict to a smaller class of spaces? And I would say, roughly speaking, there are two schools of how to do this, which are overlapping. One I would call the exodromical approach, and I won't say anything about this because I hope maybe Clark mentions it or maybe he doesn't, and then you can ask me about it. So this sort of roughly has the idea that we should understand stratified spaces in whatever encodes the category of constructible sheaves on this, and that gives you the stratified homotopy type. And then there's sort of the old school direct approach, where we would say, okay, stratified homotopy theory should be the study of certain stratified spaces up to certain notions of equivalence. And there again, you have two ways of playing the game. You can do it classically, so you do it geometrically. You just restrict to nice spaces, or, and that's probably equivalent, we'll get to that, use a more flexible notion of stratified equivalence. And right, by the standard procedures and model categories or the way localizations behave, these two probably end up with the same type of outcome. So I want to talk a bit more about this approach today and how it relates to the stratified homotopy hypothesis. And to this end, let me maybe start with sort of the first approach, namely stratified spaces, diagrams of spaces, or as pre-sheaves on the subdivision of a poset. I will explain in a second what that means. And this all goes back to a, let's say, fairly standard technique that people have used in stratified geometry and stratified differential topology for a long time. Namely, the way people work with stratified spaces is usually you want to sort of make arguments stratum by stratum, but that isn't quite enough. And you also need to consider the way these strata interact, the so-called links. And so what you do here, what you can do is you can take a stratified space, you can take its minimal element or minimal stratum here, or just some stratum in there. Here you have the p stratum. Then you, as a complement, you have everything living above the p stratum, so the union of all strata over p. And then in between you have the so-called link, which is, roughly speaking, the regular neighborhood of the stratum, the boundary of the regular neighborhood of the stratum in here. In the smooth setting, and then you can decompose your stratified space into these pieces. So here you have the two strata, let's say in the two stratum setting. And then in between you have this link, and there are maps from the link down to the singular stratum, which turn out to be stratified fiber bundles. So there's some type of fiber bundles, and their fiber is itself stratified. And so in this fashion, you sort of have a tool to decompose these type of nice geometrical stratified spaces, so-called Whitney stratified spaces. Didn't explain what that is, but think of it as a smooth version geometrically. Of course, if we want to do homotopy theory, this type of approach isn't all that nice. I probably won't get these geometrical links. They won't be functorial. It can all be quite difficult. And so Quinn, and I think partially also Huge, came up with a homotopical version of this type of diagram. And what they did is they replaced this link here in the middle with the so-called homotopy link. And the homotopy link is, again, a stratified space. It's just the stratified space of paths which start in the P stratum, the P homotopy link, and then immediately exit into another stratum, the so-called exit paths, or paths like this. And it turns out that at least if you work with nice stratified spaces, this map here isn't quite a fiber bundle anymore. The starting point evaluation map sending a path to its starting point. This isn't an inclusion, that's a typo. To its starting point, but it is at least some type of stratified fibration, right? And this led to Quinn's definition around the 80s of a so-called homotopically stratified space, where he said, okay, I don't really want to deal with these stratified fibrations. I don't quite know how they work. Because he was extremely smart, he figured out I can just do it with pairwise stratified homotopy links. So I just look at the Q stratum of the homotopy link, which at P, which are the paths that start in P and exit into Q. And he said, I will call a space homotopically stratified if the map from the homotopy link from P to Q into XP, sending a path to its starting point, is a Urevich fibration. This only works for metric spaces. Then there's an additional cofibrancy condition on pairs. But you can see how this really leverages this type of geometric observation with the fiber bundles and pushes it into a homotopy theoretic setting. And it turns out that essentially all sort of geometrical examples you could think about fit into this class. And you can actually do reasonably well homotopy theory with these. For example, Quinn developed a whole sort of surgery setting together with Browder for these type of spaces. And in 2013, Miller proved that they actually admit some type of Whitehead theorem. So if you work with a stratum-preserving map of homotopically stratified spaces, so a map that over some fixed P, and it induces homotopy equivalence of the strata and the pairwise homotopy links, that's exactly like a condition that characterizes stratified homotopy equivalences. So this also already gives you hope that you could maybe find a weaker definition of equivalence of stratified spaces, which comes down to the same definition for classical examples such as conically stratified spaces. Now, this type of result gave rise to a new approach to the stratified homotopy theory. And I would say this was around 2016, 2017. When did you start your PhD, Peter? 2016. So it was around this time, and I think three groups of people, three PhD students independently started working on this. So it was Peter, it was Sylvain Dutot, and Stephen Donald without knowing of each other, right? So this was, or did you know when you started of Sylvain and no, right? So I think all of them started working on this related question using these type of tools maybe to define a notion of weak equivalence. There were different perspectives, maybe some more infinity categorical, more diagrammatic, but at least Peter and Sylvain, I think, ended up observing something very similar. Probably also Clark was involved in this. And this was not the definition that they gave, but I will get to the one in a second. So what we have for stratified space is we already have seen that we can decompose it sort of inductively by taking the strata, the sort of minimal stratum here, then everything above this stratum, and then looking at these stratified homotopy links. And so we could just define a notion of weak equivalence inductively using this by saying, okay, for a trivially stratified space, an equivalence should just be a weak homotopy equivalence. And then inductively, I say, oh, the diagrammatic equivalence for a space with n+1 strata is just one which induces weak equivalences on the strata, then on the piece above, so everything above that stratum, which is a stratified space with n strata, and on the homotopy link, which is also a stratified space with n strata. This is sort of the minimal inductive definition you come up with. And you can imagine this is a mess. Because if you use this definition, every proof is inductive, and you have to take the homotopy links of the homotopy links of the homotopy links. You don't want to do this. And there was a nice observation that people made, which was, oh, we can actually replace these iterated homotopy links with these type of spaces. So if you sort of several times take the homotopy link, this type of space is equivalently given by you take the topological simplex, you use a flag here to specify the stratification, and then you look at the space of maps from that stratified simplex into X. So for example, if I do this with by a point, so just one stratum, I just recover the stratum. It's maps from the point with that stratum into X. If I do this with paths, so I equals a singleton here, a tuple here, then I just recover the ordinary homotopy link of such paths which end in the Q star. And now we can, of course, give a nicer definition, namely a diagrammatic equivalence should just be a map that induces weak equivalences on all homotopy links. And that definition was given by Dutot and independently Enriquez, a fourth person who was also thinking about this question, but not during his PhD.
Well, it was during his.
It was during his
But
PhD.
it was like more than a decade earlier.
Oh,
So
but not published, I guess, right? Yeah.
not published. But I told Sylvan about this actually.
Yeah. I think I think he's ended up coming up with the same definition independently. And then,
We also did something else with this, but it was in a just purely infinity categorical sense. Yeah.
right. I mean, you will also, I guess, you'll show up in a second with that definition.
Something which was not, I mean, a priori not, you didn't need to know anything about topological spaces, but still using basically the same definition.
Right, but now we can just use this equivalent definition that's a lot more concise. And we can ask ourselves, does this lead to a good homotopy theory? Well, at least what holds is that this fulfills some type of Whitehead theorem. So if your stratified spaces can be triangulated and they are, let's say, conically stratified, then this notion of equivalence is equivalent to stratified homotopy.
Would it be unreasonable to ask you to draw like what one of these one of these generalized homotopy stratifications looks like?
Would it be unreasonable to ask me to draw a homotopically stratified space?
Like where
Kind of.
it's not a point. Like, could you do it with 2 points to sort of illustrate what the paths look like in the homotopy link?
Oh, the homotopy link, of course. Yes. I mean,
Just not like
the paths in the homotopy link are still the same, right? I mean, let's say we draw something like, maybe my stratified space looks something like this. Right, so these type of leaves intersecting here. And this is my singular stratum. And then the homotopy link between these two would really just be the space of paths, which start in here and then immediately exit.
but if I is like 2 things, what if
If
that
I have 2 things, okay, then I need a third color, which I don't have. So in this case,
The basket in that,
oh, there's some color.
to the side of the,
yeah, perfect. In this case, let's say it would be maps from the stratified 2 simplex. So let's say my simplex is stratified like this. And let's say I stratify by putting another singular point here, right? And then it would be maps from this simplex in here, which preserve the colors. But we'll get rid of these in a second. The nice thing, it's another nice observation.
Sorry, can I ask one more question? Is there a reason that you don't want, like, I think, so you could also just look at an interval where you've broken it up, like,
We get there. That was a very good anticipation. We'll get there. That's one way of thinking about it. Maybe another thing to notice about this definition, the nice thing is that all of these homotopy links, they arrange into a nice diagram like this, right? So what I can do is I can just restrict along the inclusions of these stratified simplices, and then I get a huge diagram which is indexed over the subdivision of the poset, which is just the set of flags in the poset P. So I end up with a sort of base valued presheaf or anima valued presheaf on this SDP here. And it turns out that is essentially all the information in that homotopy theory. So this was a result of Sylvan Dutot, which ultimately said that if you localize stratified spaces over a fixed poset P at these diagrammatic equivalences, and then this homotopy link functor just gives you an equivalence with presheafs over SDP. Now this is in one sense a nice answer, and in the other sense it's a bit of a disappointing answer, right? Because it's extremely powerful, but it also tells you that your stratified homotopy theory might not be super deep or interesting to study if you end up with this, I guess, depending on your examples. So it's very tractable, as I mentioned. It also has some fairly nice properties. In joint work with Sylvan Dutot, we proved that there is a type of stratified Kant-Quillen equivalence with stratified simplicial sets. And it has a fully faithfully embedded category of PL conically stratified spaces. They sort of all live in there, classically. But one thing I want you to observe is that somehow Quinn got away with just using pairwise homotopy links, right? And this goes very much in this direction of that question. And this was, I think, also something that was specifically observed, I think, first by Ayala, Francis, and Rosenblum, and then also in these exodermy articles. We can probably localize more than that while preserving the stratified homotopy type of geometric links. And this comes to the following insight. I'm not sure who to date this to. Maybe you can help me out. So it certainly was observed in some shape or form by Miller in his work on stratified homotopy, on homotopically stratified spaces. Certainly also in your work, Peter. It's also certainly in the exodermy article. I think it somehow shows up a little bit in the stratified homotopy hypothesis by AFR.
Yeah, certainly they were aware of this. Yeah, I mean, everyone knew about it. But yeah, it seems like it.
So I guess here's something that everybody knows. If you have a nice stratified space, let's say homotopically stratified or conically stratified, then the natural restriction maps, which send such a stratified simplex in here to this pullback, and if you look at what this pullback is, it's paths from P0 to P1, pullback over P1 to, and so on. These are really essentially sequences of stratified paths sort of glued together, right? This is really what she said before. This turns out to be a homotopy equivalence. And this property of this type of diagram is called being a decollage, as opposed to décalage. Mind the O here. Is there a French person in this room who can explain the difference between a décalage and a décollage? I guess décollage is some type of art project thing where you like cut things apart and then glue them back in, right?
Décalage is shifting.
It's shifting. Yeah, so completely different form. Great. All right, and if we denote the full subcategory of such things by dec P, then it turns out, I think this actually goes back to you, this is a left localization, right? So this has a left adjoint functor, this inclusion. And that exposes décollage as a left localization of this pre-sheaf category here. And now you can give the following definition of what an equivalence of stratified spaces should be, which I think goes back to you, Peter, but you didn't explicitly spell it out. But if you like really read your article carefully, I think this is the class of weak equivalences that you ultimately define, right? You phrase it as an existent statement. It's a stratum preserving map of stratified spaces should be a so-called categorical equivalence. I want to distinguish from the diagrammatic ones. If you take this homotopy link functor, and then you're an equivalence in this localization. So after applying the left adjoint to décollage. This is fairly indirect, but it works extremely well because as a corollary of Sylvain's result, you immediately obtain that stratified spaces, if you localize at this class of weak equivalence, you get an infinity category equivalent to décollage. Right? Because you, yeah?
Sorry.
No, go ahead. Okay. Just because there was all things going on at the same time, just remind me of what this homotopy link is for a stratified space. Is it so I fix a flag?
The whole homotopy link, like this whole thing, is the whole diagram here. That's just a notation to have all of these homotopy links in one diagram. That's what I mean there.
So do I just have a co-simplicial object in stratified spaces and take the nerve with respect to that?
Almost. If you,
But it's relative with respect to the.
it's relative with respect to the stratification, of course. If it's sort of almost just a simplicial object, yes.
Parameterized over like flags.
It's parameterized over flags and as opposed to, yeah, just normal simplices, yes.
And that
But you
could
can
be
give a
sort of
version
like-
that is just co-simplicial and where you use sort of
Yeah.
not stratified spaces over a fixed poset, but you use all stratified spaces. And there you can give it a different thing. That also works.
Okay.
So the question was, what exactly is yeah,
Dec P is this category of these décollages. So like all diagrams in this category of pre-sheaves, right, which have this décollage property.
okay, I understand. Yeah.
Yeah. Okay. Right. So this is something that we can use, but somewhere in the very beginning of the talk, I promised you a stratified homotopy hypothesis, and maybe this definition of a weak equivalence isn't super enlightening yet. I mean, that I guess depends on how familiar you are with decollage, but I would say we can maybe try to look for a definition that is a bit more intuitive. So this is the next step, namely going to a stratified homotopy hypothesis. Roughly speaking, how could one even come up with this type of idea of a stratified homotopy hypothesis? Well, let's suppose we have some homotopy theory of stratified spaces, maybe the one from the previous page, but now we allow the poset to vary. We can think of trivially stratified spaces as living in there. And we know that trivially stratified spaces are equivalent to infinity groupoids. And those live in infinity categories. So maybe stratified spaces are equivalent to some larger class of infinity categories. We can ask that question. And the first version of such a theorem was obtained in this article by Ayala, Francis, and Rosenblum called the stratified homotopy hypothesis, where they obtained such a result for a geometrical version of stratified spaces called so-called conically smooth stratified spaces. And they obtained a fully faithful embedding of such spaces into everything. And then they asked the question whether there's a topological analog of their result. Like, instead of using these conically smooth stratified spaces, can I do something with all stratified spaces and then maybe even obtain a nice equivalence where I can characterize the essential image of stratified spaces? And to explain how this type of equivalence should even come to be, what I should do is I should give you an analog of the infinity groupoid of paths here. Right? So what we now need is we need a stratified analog of this infinity groupoid of paths. And that is the so-called infinity category of exit paths. And this idea is quite old. I think it goes back to McPherson, an unpublished work where he defined like one category of exit paths. And then Jonathan Wolff and Truman gave explicit definitions, one as a one category, one as a two category of such exit paths. It turns out, since we're sort of in the homotopy theorists world here, we can just immediately give an infinity categorical definition. I won't even bother with the one categorical one. And at least for a nice conically stratified space, it's given as follows. You take the stratified realization functor, now we come to this co-simplicial object in a sense, which associates to delta n the stratified realization, which I described before, and then you just take the associated nerve. So you take the associated thing. And it turns out, at least for conically stratified spaces, this gives you a quasi-category. Okay, well, maybe not so helpful yet. Let's maybe look at an explicit example of what this infinity category of so-called exit paths looks like. Why are they called exit paths? And this just comes down to the following. Well, let's first look at what are the objects. Well, the objects are just stratified points, right? So these are just points in that space. Nothing to be seen here. Up to equivalence in the strata, I have 2 points in this space. And then what are the morphisms? Well, the morphisms come from this stratified simplex over here. They are maps from this stratified simplex into this stratified space. And there are essentially 3 ways I can map this. I can map the red and the blue stratum into the same stratum, red or blue. Then I just end up with ordinary loops, either at the red point or at the blue points here. So this gives you this part and this part. Or I have paths which start in the red stratum and go into the blue stratum, the proper exit paths. And they give me this path and this path. And so the exit path infinity category of this pinched torus here actually turns out to be a 1 category. And it is given by these generators A, B, A prime, and B here, and these relations. Fairly simple. Now, one observation you can make here is that this category has the property that every endomorphism is an isomorphism. And that's sort of tautologically true, because if it's an endomorphism, the starting point and the end point are in the same stratum. So the whole path is in the same stratum. So it's just an ordinary loop, and I can just take the inverse parameterization, and I have an inverse. And such infinity categories were called layered. I'm not sure where that term came from. I read it in exonomy first, and then.
That's nerdy.
What? That's
That is
Nadine?
nerdy.
Ah, okay, great.
We asked people what to call this because somehow stratified seemed to introduce too much confusion, and he said we should say that.
Okay. So I should put Nadine somewhere. And I'm going to denote by lay infinity the full subcategory of such things. And then there's another word which can also be useful, namely of so-called abstract stratified homotopy types. This is sort of what happens to a layered infinity category after you stratify it. And this is just an infinity category with a conservative functor into a poset. And conservative functor, if you think about it, into a poset, that really just means that the fibers of this functor are infinity groupoids. And that's also what happens here, right? So every endomorphism, infinity groupoid, the strata are spaces, they're just infinity. Right, and then here is actually the first proof of the first answer to the stratified homotopy hypothesis. So this was proven by Peter in 19, or probably earlier, but published in 19, I guess. Namely, if you localize these categorical equivalences, these decollage equivalences from before, you can actually obtain an equivalence of infinity categories with abstract stratified homotopy types. And the equivalence isn't directly constructed in terms of this singular simplicial set. Instead, the proof goes somewhat like this. I hope I don't misquote you here. Well, first off, we leverage the fact that we already know that we're equivalent to decollages. And then if you look at this decollage condition, it's some type of Siegel condition, right? It's really the type of condition that shows up when you try to define infinity categories as complete Siegel spaces. And that's the nice thing, like the really neat thing about this proof here, you don't have to deal with the topology anymore. These are all just some type of infinity categorical objects. And then you leverage the classical equivalence between complete Siegel spaces and quasi-categories to obtain this type of equivalence here. And so your equivalence really goes to the homotopy link construction. Then you do some type of localization to decollage, and then you lose an equivalence here, which gives you an answer to this homotopy hypothesis.
Lurie's result was for conically stratified?
Lurie's result was just that these things have a quasi-category, and then he proved an version of monodromy called exodromy for these things. I think there's nothing in there that really defines a homotopy theory.
Okay.
It was really just,
This category of stratified spaces on the left has.
This is all of them.
Conical, yeah.
no, all of them in there, but then you have to do some type of localization going down to decollage to. Now, this is an extremely neat answer, I would argue. One corollary that you get is also a global version of this result, where I sort of don't fix the poset. And I'm not going to really define what it is here, but from this you can derive that there is a class of weak equivalences for stratified spaces, such that if you localize them sort of globally, not fixing the poset, you get layered infinity. When I first stumbled about this result, I was extremely happy and not 100% happy, which was probably because I didn't know so much infinity category theory back then. And I would have kind of liked to have this equivalence be presented in terms of the stratified realization of the singular simplicial set. Right? I think even now that I know more infinity category theory, I would still like it to be presented in terms of this adjunction. But I would say one of the selling points of the Quillen's interpretation of the classical homotopy hypothesis is that you have this really nice classical presentation. So you could ask, can we actually just use these two, right? And then another question you could ask is, can we find a bit more of a natural characterization of this W cat here, this WP cat, instead of this decollage condition? And in fact, for nice stratified spaces, so let's say for conically stratified spaces, Peter gave such a characterization that he said, well, if there's Sing S is Joyal fibrant, then something is in W cat if and only if the Sing S is a Joyal equivalent. So if and only if it's an equivalence of infinity categories. And here the third guy who was working on these questions comes in, Stephen Nondlal, a student of Jonathan Wolff, who said, well, honestly, I'm just going to try to use this as a definition without being aware of Peter's work, actually. Like independently, he said, I want to use this as a definition. And he ultimately conjectured that what he had defined should probably be the same. There should be no fibrancy assumptions at all. So for all stratified spaces, and it can actually be relevant to look at other stratified spaces, this type of characterization should hold. So these categorical equivalences with this homotopy link decollage thing, they're just the ones whose singular simplicial set gives you a Joyal equivalent. It turns out this is true. This followed from some work that I did together with Sylvain Dutot, where we really looked at this other stratified homotopy theory. So not localizing to decollage, but once you understand that one, the other case essentially also follows. And in fact, we proved that the stratified adjunction has the following properties. Of course, there we had to get our hands dirty and do some topology. We couldn't do it purely on the infinity categorical side. First off, these categorical equivalences are precisely the maps for which Sing S F is a Joyal equivalence, which is also equivalent to it being an equivalence in the localization of this model structure, of the Joyal model structure that gives you layered infinity categories. And then also conversely, something is a weak equivalence in this model structure that gives you these layered infinity categories, if its realization is a categorical equivalence. And if you've sort of played around with this yoga a bit, these types of two statements are actually equivalent to both unit and co-unit being given by weak equivalent in this setting. So this is one of these cases where somehow you have this extremely nice setting where you don't need to derive at all. even though things aren't necessarily cofibrant-fibrant in the appropriate sense, these two functors, they immediately descend to infinity categories. There's no need to derive or anything. You can just throw them onto the setting. And in particular, we then get this junction here between stratified spaces, localized at categorical equivalences, and equivalence with layered infinity categories, which is explicitly presented by this adjunction here. Great. So that's how far we got now. I guess we have one answer to the stratified homotopy hypothesis now. And if you are sort of a very modernly minded infinity categorical person, you're probably happy with this, right? Like this is all you ever want to know about this. Now, if you're a little bit more like sort of classical people within the stratified spaces community, you might complain, why is this thing rightfully called the homotopy theory of stratified spaces? And you will get some good answers to this. I think we will get a good answer, maybe not. I'm not sure what Clark's plan is, but you can get good answers for this from the exodromical perspective. But you could also ask, how does this theory here really relate back to these classical geometrical examples? And classically speaking, these type of relations were induced by model structures, or like at least the techniques that showed up in model structures, right? So a question that was open for a while is, how can we really relate this back to the geometrical set? For example, very simple question. I have, let's say I have two stratified spaces, which are nice, geometrical, classical, conically stratified, maybe PL or something like this. What is pi0 of this mapping space? I can, of course, give you the answer that I just go over to infinity categories. I compute the pi0 there. But like topologically speaking, I would expect this just to be the set of stratified homotopy classes, right? So does this hold true, for example? And in fact, the goal of sort of Stephen Lal's thesis, without even being aware of these other things, was really trying to transfer the Joyal model structure along this adjunction over to stratified spaces. And in fact, if you could do this, then it would turn out that you have these type of nice characterizations, right? So then you have really good control over all of your classical geometrical examples. So if you are not so familiar with this technique of transferring model structures, the question really is there a model structure for this homotopy theory that I have defined such that practical examples are bifibrant? That's the question. And Stephen proved that you can define a model structure, but not on the whole category, just on the ones which sort of have a fibrant associated stratified simplicial set. This isn't enough for the stratified homotopy hypothesis. For example, it doesn't give you fibrant replacement. You don't get an equivalence of the two theories. And so he conjectured that one could, in fact, be able to extend this to the whole thing. It turns out, sadly, the answer is no. There does not exist such a model structure. Let me maybe quickly give you an idea how this example works. So if we had a model category, then what we would get is that if you have a Joyal equivalence, acyclic Joyal cofibration here, you realize it, you push it out, then this map of stratified spaces should be a categorical equivalent. And here is the example of a horrible space that does not fulfill the property. It's here just a triangle with two strata, one in purple, one in red. We have one piece of the red stratum is just this line. And then we have sequences of points on the left-hand side and on the right-hand side converging. And you can make a bit of an, but this is a posed stratified space. Maybe this tells you that there are a lot of posed stratified spaces. And you can make an argument that if this type of condition held, it's fairly easy to figure out, then the map that collapses this red line to a point would be a categorical equivalence. Would have to be the case. But now on this right-hand side, you have these exit paths which oscillate back and forth between the red points. And because we're stratified, we can't pull this path in, right? We can't pull it all the way in. We can only pull it away from finitely many of these oscillations here. And here you have this red line, and it prevents you from going back and forth. So this turns out to be a counterexample why the model structure can't exist. And I think Stephen was already kind of aware of this because he just said, well, probably it's just a left semi-model structure. If you don't recall what a left semi-model structure is, don't worry about it. Roughly speaking, every condition that involves an acyclic cofibration should have cofibrant source. And these things are just as good as model categories. Like, I don't know of a statement that doesn't in practice hold.
I guess you don't quite have a 3-arrow calculus of fractions, right? You have like a 4-arrow calculus of fractions.
Right. Yeah. I mean, you lose some symmetry. I think that's the main price. You lose some, like, if you want to bifibrantly replace an object in a model category, you can either go fibrant and then cofibrant, or the other way around. Here you have to go cofibrant first. That's really the price that you pay. For everything else, they're just as good. All of the theorems in homotopy theory and model categories essentially have analogs for these things. And it turns out that such a thing exists. And if we actually look at how this proof goes, this type of push-out diagram from before, it's really the only obstruction. And if you look at it in a semi-model category, I need this type of push-out condition to hold only when this thing is cofibrant. That's the only difference, really. And this turns out to be the case. So if you have, let me see. So we only need to do this for cofibrant things. These are roughly stratified cell complexes. So retracts of spaces which can be glued together from stratified simplices, stratifiedly. And for those spaces, we can now make the following argument. Well, we know our theory is a left localization of this presheaf category. The equivalence comes from the homotopy link functor. So to check that this diagram is homotopy pushout, has the correct properties, I just need to check that it is a pushout diagram after applying these homotopy links. So now what I need to do is I need to compute the homotopy links of stratified cell complexes, right? To actually prove this type of statement. And it turns out in the PL setting, so if everything is PL, all of the maps, everything is piecewise linear, triangulated, then these homotopy links are just given by the classical PL links. So roughly you take a first derived neighborhood, and then you take the boundary of that, as indicated here. And there the statement then becomes obviously true because these PL links preserve pushouts and cofibrations. Now, in the case of stratified cell complexes, the whole thing turns out to become a lot more technical. And I mean really technical. I think, I don't know, this is like 50 or 60 pages of like really being extremely careful with set theoretic topology, 30 pages of combinatorics, and then you really, really have to check that the map is continuous. You write down the map and you're like, oh my God, like this is only defined in certain places. I divide by 0, do I? I don't know. Is this thing continuous? You know, like that's the proof. But then you can ultimately show the same type of statement holds for stratified cell complexes. And that actually gives you get a left semi-model structure. So the Joyard model structure transfers over, and you actually get a sort of model categorical version of the stratified homotopy hypothesis, which tells you this equivalence here is this junction here is equivalent equivalence. It's even equivalent equivalence that creates weak equivalences. So something is a weak equivalence if and only if. That's way better than an ordinary equivalence. There's no need to derive. And then this equivalence actually presents that homotopy theory on stratified spaces that I guess Peter defined ultimately. Right. So this gives you an answer. I promised I would ultimately tie it back to the geometry. So the last thing I have to do is explain how this model structure helps you connect to geometric stratified spaces, or like classical geometric examples. If I say geometry, I think I mean something that comes from the world of geometry. I think Lark meant more something like that. It's something that is actual geometrical, like has an extra structure. But I mean manifolds. That's what I mean. Something like manifolds, but with singularities. Okay, so what are the bifibrant objects? Because those are the ones that are usually best behaved in a model category, right? It turns out they are retracts of so-called CFF stratified spaces, allow the pun. What are the conditions? Well, I will call a stratified space CFF stratified if it admits a cell structure compatible with the stratification. First condition. The strata are connected, and the stratification comes from the frontier condition. So this is actually kind of interesting, like this really old school frontier condition of Whitney from, I don't know, 50s or 60s. It shows up here. And then that thing as X is a quasi-category, which actually turns out for metrizable scenarios to be equivalent to the pairwise homotopy link maps being fibrations. This is surprising because the condition of Lurie's really involves multiple strata. Like checking that these thing S are quasi-categories, that involves checking multiple strata. We only need 2 here. And this is also a fairly involved proof. You really need metrizability, otherwise it's false. But this is why Quinn was able to get away with just having pairwise homotopy links. Well, this is also an extra theorem you need to prove, I guess. And in this class, so example, all Whitney stratified spaces, if you recall what those are, maybe you don't, not so important, but every thing arising from algebraic geometry can be Whitney stratified, for example. these pseudo-manifolds that people are studying in intersection homology. All of these are CFF stratified. And then topological pseudo-manifolds are CFF stratified if retracts of CFF stratified if they admit mapping cylinder neighborhoods. That might not be the case. There are some fairly topological pseudo-manifolds. And then finally, these conically smooth stratified spaces of Ayala, Francis, and Rosenblum, they are also retracts of CFF stratified spaces, assuming that their unzip theorem holds, which might need some fixes in the proof. And so what you ultimately end up with is sort of a really classical version of the stratified homotopy hypothesis, which tells you that a CFF stratified space, that you take CFF stratified spaces, you just localize the ordinary stratified homotopy equivalences, so old school CW complexes homotopy equivalences, and you end up with layered infinity. So this is actually something you can tell to somebody who doesn't do higher category theory, doesn't know what a model category is, has just read sort of old school algebraic topology, and you can say, well, it's these things, they are essentially Quin's homotopically stratified spaces plus cell structure, and then you replace your Revich condition by CF vibration, right? And then localized stratified homotopy equivalences, that's the same thing as layered infinity. Right, so here, maybe to end the talk, some consequences. For example, for nice stratified spaces, we can actually compute pi0 of the mapping space. In fact, we can compute the whole mapping space now. And it's just at pi0 level, just stratified homotopy classes. So it's fairly easy to understand. If supposing the smooth stratified homotopy hypothesis of Ayala, Francis, and Rosenblum, we also get smooth stratified approximation for free. So we get that the mapping space of stratified maps is equivalent to the mapping space of smooth stratified maps in this language of conically smooth stratified spaces, just by passing through the infinity categorical world. So this is actually something you could use in practice. It tells you every continuous map of conically stratified spaces can be approximated by a smooth one. We can use this to construct classifying spaces. And then, and this was, I guess, sort of a large part of my PhD thesis, at least the second half, you can use this to define a stratified version of simple homotopy theory, which for these type of tools, you really need a model structure, at least for what I did. I guess there are smarter ways of doing it. Right, and you can even use it in TDA to get invariants for singular data sets, if you're interested. So that's it. Any questions?
Let's thank the speaker and then